Hi, welcome to this video, which is today a small sample calculation related to the previous video about the Richard-Zaki equation, and therefore we have the following plan, and this is that we look at a very simple task of swarm settling. This is one task from the previous video about train your knowledge, and therefore we repeat the Richard-Zaki equation shortly, and then we use this to calculate the given task. And finally, we will also have some few more questions just to understand this Richard-Zaki equation even more. So if we take a look at the task, which is about swarm settling of sand particles, so we have a suspension which contains spherical sand particles, and they have a diameter of 100 microns, and they are suspended in water at 20 degrees Celsius. And this is basically what you see here, right? So this is a thickening tank where the sand slowly settles down, and the solid volume concentration is 0.12, so 12%, and the density of the particles is 2,650 kilogram per cubic meter. And density and viscosity are respectively, the density is 998 kilogram per cubic meter, so very precise, and the same for the viscosity, which is 1.002 10 to the power minus 3 Pascal seconds. And with all these numbers, which are very normally known, right, the size, the concentration, viscosity, density, it's easy to get these numbers. You are asked to calculate the swarm settling velocity of these particles. So how fast will the particles settle down in the thickening tank when we consider the full swarm of particles? And therefore we need the Richard-Zaki equation, which I introduced in the previous video. And this is the most important and mainly used model to describe these swarm settling velocity, which you see here. And basically this works for concentrations till 0.3. If we look at the task, we have a concentration of 0.12, so it works perfectly. We are completely in the range. Sedimentation is also in the given task, so we can use this model. And basically the ratio of swarm settling velocity to terminal velocity equals 1 minus concentration, and then the exponent, which I will repeat in a second, which goes from 2.4 to 4.65. And since we want to calculate this value here, we need to multiply by terminal settling velocity, and then we have the swarm settling velocity equals terminal settling velocity times this part here. So we need to calculate the terminal settling velocity. We know this already, and for the exponent, okay, sorry, this will come next. I was too fast. So first we need to calculate the terminal settling velocity. About the exponent we will talk in a minute. And to calculate the terminal settling velocity, you already have some knowledge, and basically we have to make an assumption. And the assumption, the easiest assumption, is we have slow settling generally, so we assume that we have Stokes regime, right? And Stokes regime means that we can calculate the terminal settling velocity by this equation. There is also a previous video where we derive this equation, and multiple videos where we really go into the details why the equation looks like it looks. And what we need is the density of the particle minus density of the fluid, g, size of the particle squared, and here's the viscosity of the fluid times 18. And we have all these numbers, luckily, so we easily can calculate this. So 2,650 minus 998 multiplied by g, 9.81, multiplied by 100 microns, so 100 multiplied 10 to the power minus 6 meters, and this is squared, and then they divided by 18 multiplied by the viscosity. And when you put all of this into your calculator or whatever, you will end up with 0.009 meter per second. So this is the velocity of one individual particle which settles down under the given conditions, assuming Stokes regime. And now we have to be careful, because we don't know if Stokes regime is a good assumption or not. And therefore we can check it by using or by calculating the Reynolds number, because the Reynolds number will tell us if this is a good assumption, and the Reynolds number is the velocity, density of the fluid, size of the particle, and viscosity of the fluid. Density of the fluid we know, size of the particle we know, viscosity of the fluid we know, and velocity of the particle we calculated, right? So we can put all the numbers in, 0.009 meter per second, 998, then the size, and here we have the viscosity, and this will end up with a Reynolds number of 0.89. And this is a very interesting result, because Stokes regime can be used till a Reynolds number smaller than 1. So we can make a check. We are smaller than 1, Reynolds number works very well. However, you find sometimes that Stokes regime only works till a Reynolds number smaller than 0.25. And this is because between 0.25 and 1, the error goes a little bit larger. And this means that the velocity of the Stokes regime can be used, but is not perfect. And therefore, as an additional task, you can keep this in mind. I will talk later a little bit about it, but so far generally we can say Stokes regime work, it's good, we're below 1, generally we can use it, so we can work with this velocity. And now we have to look at this exponent, and maybe you remember this graph, and depending on the Reynolds number, the exponent changes from 4.65, then it decreases to, when you are at very high Reynolds numbers larger than 500, 2.4. But we are below 1, so we can say our exponent is 4.65, and then we have all the numbers we need, and we can rearrange the Richard-Zaki equation. And with this rearranged equation, we just put all the numbers in. This is the terminal velocity from Stokes. This is the concentration. This is the exponent based on our Reynolds number. And then we will get a velocity, a swarm settling velocity, not of an individual particles, but the swarm of particles settles with a velocity of 0.0049 meters per second. And this is a very different value than 0.009. So we can relate these two, and we see that the swarm settling velocity is decreased by 54%. So if we consider that the particle is not alone, but there are multiple particles, the velocity of the particles for this case is decreased by 54%, sorry, just because of the presence of other particles. So using the individual, the terminal velocity, is not a good approach to correctly calculate the time the particles need to settle, because they are much, much slower. Okay, and if you want to go a little bit further, then you can consider that we are with our Reynolds number not below 0.25, and there are models which you can use. So you can take a look at the models when you are between Stokes and Newton regime, and there are models you can use to calculate the terminal velocity, which is a little bit different than this value. And then you can see, this is a task for more interested students, but then you can see how this value will change when you highlight more that the Reynolds number is larger than 0.25. But generally you will see this is a proper result already. But if you're interested in this, I really recommend to look how you calculate the terminal velocity when you are a little bit larger than Reynolds number a little bit larger than 0.25. Okay, then I just have, for a little bit better understanding, also some questions. So here's the Richard-Zaki equation. And the question is, which of the following trends is correct? Increasing particle size always increases n. Sorry, there's a typo from me. With n is alpha, it's the exponent. So I'm sorry for this. Increasing solid volume fraction decreases the particle swarm velocity. For dilute suspension, swarm velocity goes to equalizing to terminal velocity, and exponent n again, so I'm sorry, exponent alpha depends on Reynolds number. Okay, let's take a look. Increasing particle size will always increase the exponent. We saw that increasing particle size will increase the Reynolds number. And with increasing Reynolds number, the exponent decreases, not increases. So A is not correct. And it's also not always the case, because we have regions in the diagram where the Reynolds number increases, but the exponent does not change. So there are areas where it changes, and then it decreases with increasing Reynolds number, so with increasing particle size. And there are regions where nothing changes. So this is not correct. B, increasing solid volume fraction decreases the swarm velocity. So let's take a look. If we multiply by Vt, this goes here. And if we increase this number will decrease, right? So increasing here will decreasing this one. And when this one decreases, this one will also decrease. So this is correct. For dilute suspension, the swarm settling velocity will equalize the terminal settling velocity. So again, we multiply by the terminal settling velocity. Dilute suspension means this goes to 0. If this here goes to 0, this full term goes to 1. And if this goes to 1, this equals this one, right? So this is also correct. And the exponent alpha depends on the Reynolds number. Yes, for discussing type A, we already saw this dependency. So B, C, and D are correct. A is a not correct trend or state. And then we have a second question, and this is the question, very simple: in which industrial operation is the Richard-Zaki correlation particularly important? Gas compression and pipelines, sedimentation tanks and thickeners, heat exchangers, centrifugal pumps. And this is very easy. It's of course B. I also gave you in the videos and also here the example of a sedimentation tank or thickener. So B is the correct answer for industrial operations in which we use the Richard-Zaki equation. So with this we are already finished, and I hope in this video you understood the task we look at. We try to repeat the Richard-Zaki equation and use the knowledge to solve the task, and in this way I hope you gain a little bit more understanding of the equation. And then we have some more general questions just to learn a little bit more about the equation or understand it a little bit more. And with this, I'm finished with this video and really would like to thank you for watching.